So in the last video, we discussed about finding the equilibrium points and then draw the phase portrait or the phase line for to graph the family of solutions, right? So we found the equilibrium solutions, and to find out the other solutions, we try to draw the phase portrait or phase line and then try to estimate the other solutions in the graph. And again, we will learn how to solve a differential equation, what are the techniques to solve the differential equation later. But as I mentioned in the previous videos, not all differential equations are solvable, and some of them the solution exists, but it is very difficult to solve, very hard to solve. In that case, this kind of drawing the solutions, family of solutions, using the phase portrait could be important, because you can at least see how does the solution look like, although you are not able to derive the exact solutions. Okay, so the example we discussed last time was x prime, that is dx over dt, equals to x minus 1, right? And then x minus 2, right? And then x minus 3, right? This was like x prime equals to function of x, kind of, right? Because see, on the left side there is a dx over dt, that is x prime. You can write dx over dt instead of x prime. It's the same thing. And on the right side, there is a function of x. This is autonomous because there is no explicit t on the right side. Although x is depending on t, but there is no explicitly t seen here, right? Okay, so to find out the equilibrium solution, let me write equilibrium solutions. So what we did is we said that x prime equals to 0, and then we find out the values of x. So you get x minus 1, x minus 2 times x minus 3 equals to 0, right? So if you solve it, you will get x equals to 1, 2, and 3 are the equilibrium solutions. So what do you mean by equilibrium solution? Equilibrium solutions are obtained by setting x prime equals to 0, meaning what is the meaning of x prime equals to 0? That means for any t, x does not change. X is constant. If you solve this, that is x is constant, right? For any t, x will be constant. At these values, the x will be a horizontal line for any t. Now, we need to draw the phase portrait for this to identify the behavior of the other solutions. Okay, so how do I do that? Is now we need to draw the graph of x prime versus x. Okay, so what we did is we did the graph of x prime versus x. Let me write down, this is say x, this is dx over dt or x prime. Okay, so to draw the phase portrait, what we do is we first mark these x values on this line. Let's say this is at 1, this is let's say 2, and this is let's say 3. Okay, so these are the 3 equilibrium solutions. You mark them. To draw the phase portrait, you draw a horizontal line and then mark these 3 equilibrium solutions on that. Okay, now we want to know what is the sign of x prime on the left of 1 and right of 1, left of 2 and right of 2, and so on. Okay, guys, so so on these intervals, let me say, let me write down somewhere here. Okay, so since there are 3 equilibrium solutions, there are 4 intervals, left of 1, between 1 and 2. Okay, so when x is less than 1, right, what will be the x prime? When x is between 1 and 2, what is the x prime? When x is between 2 and 3, what is x prime? What is the sign of x prime? And when x is greater than 3, what is the sign of x prime? These are the 4 intervals that is made by these 3 equilibrium solutions, right? Okay, let's go to the left of 1. Left of 1 means when x is less than 1. Okay, this line is x line. When x is less than 1, what is x prime? Let's see. Let's say x equals to, let's say 0.5. Okay, when x is less than 1, then 0.5 minus 1 is negative, 0.5 minus 2 is negative, 0.5 minus 3 is negative. So it was negative, right? So this part is negative. For x prime is negative, what does that mean? X prime negative means x is decreasing, right? Because if a derivative is negative in some interval, then the graph of the function is decreasing, right? So for the decreasing, we use this symbol there. Okay, between 1 and 2, meaning let's say 1.5 minus 1. So you can pick any test point between 1 and 2 to check the sign of x prime. Okay, I picked 1.5. So 1.5 minus 1 is positive, right? 1.5 minus 2 is negative. 1.5 minus 3 is negative. So positive times negative, it will be positive. Positive means x is increasing. For the increasing, you just draw a line draw a arrow that is going to the right. Okay. Similarly, if you pick a number between 2 and 3, you will get this is negative and this you will get positive. Okay. So it will be negative means it goes like that and positive means it goes like this. So you can think of like this. So it is decreasing. Okay. So you can think x prime is negative, right? X prime, the graph of x prime, I'm drawing the graph of that. X prime negative means the graph of x prime should be below this axis, right? So suppose this is like x equals to 0 here, and then between 1 and 2 it is positive. At 1 and 2 it is 0, right? So you need to have, it may be any like that there, so we don't know, but what we can guess is at least the graph should be on the positive side above this axis between 1 and 2. And similarly between 2 and 3, x prime is negative because we are drawing the graph of x prime, so it should be negative means it should go below that axis. And then for the other one it is like this. So you can assume the graph may be like this. Okay, now based on this, what we want to do next is we want to draw the graph of x versus t, which will be the exact solution. Okay, so this is x. Okay, let's say t is somewhere, this is t, and what we just mentioned is 1, 2 and 3 are the equilibrium solution. What does that mean? That means x prime equals to 0 at 1, 2 and 3. This is the graph of x prime. Okay, this is the graph of x prime. So at 1, 2 and 3, x equals to 1, where is x equals to 1? This is x equals to 1. This is, let's say, x equals to 0. Okay, x equals to 1, x equals to 2, and x equals to, let's say, 3. At these 3 points, x prime is 0. What do you mean by x prime 0? Derivative 0 means the function does not change, right? The function is constant there. So the function constant means when the derivative x prime is 0, then x is constant. Let me draw a constant line for that, right? So these 3 lines are constant solution. These are the equilibrium solutions there. Okay. Now we want to know how does the graph look like? Because if the graph start with 1, it stays 1. Graph start with 2. If your initial value is 1, if you say x0 is 1, x0 is 2, x0 is 3, like that, the initial condition, it is not given. That's why we are trying to find out all possible solutions. The initial condition is not given here, okay, on this question. That's why we are trying to find out all the possible solutions. All right. But if the initial condition is given, then there will be just one solution. So we don't need to do all these things. So initial condition is not given here. So we need to consider all possibilities. So if the graph starts, the initial condition means where the graph starts, right? If the graph starts at 1, 2, and 3, the solution will be horizontal lines. If the graph starts between 0 and 1 or less than 1, I would say, or let's say like this. Let's say x is positive. Okay, meaning all the values of x you need to consider is greater than 0. Okay, or you can say x0 is positive. X0 means the initial value of x, the starting value of x is always positive, meaning if you pick initial value between 0 and 1, okay, that means when x is less than 1, then x prime is negative. X prime negative means it is going down. So meaning the function is decreasing, right? The function x is decreasing there because x prime negative means x is decreasing. So x will be decreasing, increasing, decreasing, increasing, right? So anything that starts between 0 and 1 will decrease. Look at this. Let me use different color there. Look at this. This will decrease like this. Maybe this will decrease. Anything that starts here will decrease. Okay, between 0 and 1. Anything that starts between 1 and 2 will increase. Meaning if you start here, the equation will increase like that. Okay. So anything that starts increase. You see that? And anything that starts between 2 and 3 will decrease as well. So I started this one decreasing. So the solution will decrease like that. This is what is given by the qualitative analysis of the solution. Anything that is greater than a 3 will increase. Like this. Did you see that? So look at this. When the time goes up bigger and bigger and bigger, you see that these solutions are going away from this equilibrium solution, right? All the solutions are going away from the equilibrium solution. You see that? Below this, it is going away because decreasing. Above 1, it is going away as well. So this equilibrium solution is called unstable. We call asymptotically stable and unstable, because what it says is, if t is limit t tends to infinity, okay, limit t tends to infinity, and then you say that y or x here is, if it goes to a number x star, then it is called asymptotically stable. Asymptotically stable. When you go further away, when you increase the value of t, if the solution x goes to a certain solution or the certain equilibrium solution x star, in this case, what are the values of x star? 1, 2, and 3, right? When you go to the right side, or sometimes you go to the left side too, in that case, if the value of the solution goes to a certain solution or certain number, then that number or the solution is called asymptotically stable. Here, it is unstable because when you go to the right, the graph of the solution x going away from this line. But if you go right, see, all the solution between 1 and 3 go to this line. They are approaching to this line. So it is stable, asymptotically stable. And this one is also unstable. This is also unstable. Okay, guys. So this is how we categorize the equilibrium points. Some of the equilibrium points are stable. Some of the equilibrium points are unstable. There is another way of look exactly the same thing. What is that way? Is look at this here. From the phase portrait, from the phase line, you can look at that. See, one is unstable. Why? Because see, on the right side it is going away. On the left side also it is going away. So it is unstable. This one is stable. Why? Because on the left side it is going to that point. From the right side it is going to that point too. Okay, that is stable. And this one is unstable too, because on the right side it is going away. So if it is coming to that point, equilibrium point, it is stable. If it is going away, it is unstable. Okay, so sometimes you will see one is going to that point, another is going out. We call saddle. Okay, we call saddle in that case. So one way it is going in, another way is going out. So if both of them are going in, we call stable. For the stable, there is another word, stable. Sometimes we call sink, because from both sides it is going to that point, right? Sometimes it's called attractor. So attractor point or sink point or stable point are those if both of the sides it is going to that point. This is attractor, right? And if both of the sides going away, it is unstable, or we call source. Going away means source. So this is also called source or repeller. Okay, and then the stable is called sink or attractor. Unstable is called source or repeller. All right, guys. So this is how we find out, or we check. We find out the equilibrium point, and then we draw the phase diagram, and we decide whether it is stable or unstable. Let us do a couple more examples from the book. Okay. The first example I want to do is question number 2 from the book. So the question here is, find the equilibrium points for dy over dt equals to e to the y minus 1. This is given. And the initial condition lies between negative infinity to infinity. So actually you don't have to. So there is no single solution, because you should consider all the possible the initial value of y. Okay, that's what it says, because it lies between negative infinity to positive infinity. And we need to check the stability, whether it is asymptotically stable or unstable, okay, by drawing the phase portrait. All right, guys. So let us do this. So solution is, how do we find the equilibrium points? We do y prime equals to 0, right? That's the y prime. So what do you get? This implies e to the y minus 1 equals to 0. We need to solve this. What do you get? E to the y equals to 1, right? So how do I solve this for y? You can write e to the y equals to e to the 0, right? So the bases are equal. That means y equals to 0 is the equilibrium point. This is one answer. This is the equilibrium point, right? Now what we need to do is, we need to draw the phase portrait. Let me draw. So phase portrait is, along y-axis you draw the derivative y prime, and along x-axis you draw the y, right? So this cross section is not necessarily y equals 0. I can assume y equals to 0 here. It will be easier to see. Okay, let's say y equals to 0 is somewhere here. Y equals to 0 is somewhere here. Now this is the only equilibrium points. Now you need to consider that you need to consider all the possible values of the initial value of the solution, right? Initial solution, you would say. At 0, y prime is 0, right? So there are two intervals left of 0. So you see that x is less than 0. Sorry, I would say y is less than 0. So y is less than 0. What will be the sign of y prime? And then y is greater than 0. What will be the sign of y prime? We will see. And then will the solution y, because this is dy over dt equals e to the y minus 1. The solution will be y equals to something, right? And we will see whether y is increasing and decreasing there. So for y is less than 0, let's say y is negative 1. What do you get? If y is negative 1, what do you get for y prime? Is e to the negative 1 minus 1, right? E to the negative 1, that will be what? So you'll get 1 over e, that is e to the negative 1, and then minus 1, right? So 1 over e is less than 1, so it will be negative. Y prime is negative, means y is decreasing. Y is decreasing here. How about y greater than 1? Let's say y greater than 0. Let's say y equals to 1. What do you get? If you take y equals to 1, e to the 1 minus 1, which is positive, because e is 2.71, right? So which is positive. Y prime positive means y is increasing. So y prime is negative on the left, maybe somewhere like this, and y prime is positive on the right of 0. At 0, y prime is 0. We know that already. Okay. So what do you think about y? So we say that on the left side of 0, y is decreasing. For decreasing y, you write a arrow going to left. Okay. And for the right side of 0, for y greater than 0, y prime is greater than 0. That means y is increasing, right? Increasing y means we write an arrow going to right side. So what do you think? You can guess. This equilibrium point is unstable, right? Because it is source, it is going away. So the arrow are going away from that equilibrium point. Now the next thing we want to do is we want to draw the solutions. Okay, let's draw the solutions there. Let us say that y equals to, let me write down this way, and then what I want to do right is, this is t and this is y. Okay guys, now let's suppose that this is y equals to 0, This is the equilibrium solution. This horizontal line happen to be equilibrium solution. You don't have to have the same line. You can draw a t separately and then write y equals. Let's do that. I think that makes more sense. Okay. So what I want to do here is I want to draw a line, t line at the somewhere at the bottom, and then this is a t line. Okay, going that way. So this is y equals to 0. This is the graph of y equals 0 because the equilibrium points are always a horizontal line, right? So y equals to 0 is there. If you take any initial value, because we need to consider initial value everywhere between negative infinity to infinity. If you consider any initial value at 0 greater than 0, what happens? The graph will be increasing, right? So if you start somewhere here, the graph will increase. This is what the solution look like. But if you start below 0, the graph will decrease, going away again, right? Like that. So meaning this is what the solution space look like, or you can say that this is what the family of solution look like. All right, guys. So what can we say about this is y equals to 0 is unstable. Okay, guys, that's all for this problem. Let us do one more example. What I want to do here is I want to do number 6 from the book. So it is dy over dt equals to ay plus by square. So dy over dt equals to ay plus by square. We don't know the value of a and b, but what it says is a is greater than 0, b is greater than 0, and y sub 0 is also greater or equals to 0. This is what is given. Okay, so we need to find the equilibrium point, equilibrium solution. Let's say equilibrium solution. We need to find out this. We need to test the stability using the phase, phase plane, or you say phase line. All right, this is what you want to do here. Okay, let us first find out. We don't know a and b, but we know that a and b are both positive, so we'll consider some values of a and b. Okay, so and then if you change the value of a and b, only the location of the stability equilibrium point will change, but the stability does not change as long as you keep both a and b positive. Okay, so what are the equilibrium points? Solution. So y prime equals to 0 implies ay plus by square is equals to 0. So take y out, a plus by, right? A plus by equals to 0. So you get either y equals to 0 or y equals to negative a over b. Okay, that's what you get. Either y equals to 0 or y equals to negative a over b. So we want to draw the phase diagram or phase plane or phase line. So for that we need to have the value of a and b. Let us consider that a is equals to 1 and b equals to 2. We are assuming that. And we want to draw based on these values. Okay, so let us draw first y prime versus y. All right, guys, so let me do y prime versus y first. This is y prime. Let's say this is y. Okay, suppose that this is y equals to let's say this is y equals to 0, because I don't have space. I can say this is like let's say what is y equals to, what is this? This is negative 1/2, right? Because I'm taking y, a equals to and b equals to. So this is negative 1/2. So 0 must be somewhere here, right? Because 0 is greater than negative 1/2 here. All right. Now we want to draw the graph. So let us write down how many intervals are there. Less than negative 1/2, between 1/2 and 0, and then 0 greater than 0, right? Let us do that thing first. So what you get is y is less than negative 1/2, and next one is y is between negative 1/2 and then 0, and then y is greater than 0. So what will be y prime in that case? So y prime, if y is less than negative 1/2, Okay, we are taking this as 1 and this as 2. So if y is, let's say y is -1. -1 will be less than -1/2, right? If y is -1, what do you get? 1 times -1 is -1, right? And then 2 times -1 square is positive 2, right? So it will be 2 minus 1 is positive. So y prime is positive means y is increasing, right? So y prime is positive means the graph may be like this, right? So, and then y positive means the arrow must go to the right side. And I want to find out another the sign of y prime between 0 and -1/2. Let's say -1/3. If you plug in -1/3 for y, what is the sign of y prime? So 1 times -1/3 is -1/3, and then 2 times -1/3 square, what do you get? So 2 times -1/3 square is positive 2/9. 1/3 minus 2/9 will be -1/3 plus 2/9 will be negative value. So negative y prime is negative, meaning y prime will go below this axis, right? At 0 it is 0 again. And then if you take a test point right of 0, let's say 1, it will be positive. 1 times 1 is positive, 1 times 2 times 1 is also positive. So positive plus positive will be positive. It sounds like this, right? So what can you say that is between 0 and -1/2 it is negative. So y prime is positive here, okay? Between 0 and -1/2 y prime is negative. Negative means y is decreasing. For y decreasing, we draw a line with arrow going towards left, right? And then for this it is going towards right. So you can guess how does the solution look like here, right? So this you can guess, yeah, how are the solution look like. Also you can say from here which equilibrium solution is stable. This is stable, this is unstable, right? This is stable and this is unstable. Now let us draw the graph. Let me draw the graph of y versus t. So let's say this is t, okay? But you need to draw the graph only for y0 greater or equals to 0, okay? So let's say this is y. Let's say this is 0. So y equals to -1/2 is here, okay? And y equals to 0 is here, right? So anything that is starting greater than 0 will go away because it is increasing. So anything that is starting greater than 0 will increasing. Like this. At 0 it is a horizontal line. So the question is asking, you should consider y0 greater than 0 or equals to 0 only. Okay. But if you were asked like y0 between -infinity and infinity, you will have to consider the graph below 0 too. In that case, between 0 and -1/2, how would that look like? Between 0 and -1/2, it would be like this, right? If you have to draw this, although you don't have to, because you need to draw a horizontal line at -1/2 as well. Okay, it'll look like this. You see that? See, it is going towards that line. And for less than that, you see that for less than -1/2, it will go like this, right? You'd see that -1/2 is stable and 0 is unstable. But the question is asking only for y sub 0 is greater or equals to 0. So you don't have to worry about the value below that. So it will be just this is the solution. So you can say that it is unstable. So the 0 equilibrium point is unstable. You can see from this graph or that graph. Okay guys, so in the next video I will do one more example on finding the equilibrium point and drawing the phase line to determine the stability of equilibrium points. Thank you guys.